Good morning. So the topic of the presentation is the downscaling of daily temperature and precipitation in complex terrain and with deep learning methods. And this research is part of my PhD's research and benefiting from the supervision of Dr. David John Gagnier, who is a CISL faculty and one of my PhD research committee members. So to begin with, downscaling is a well-known post-processing technique that can provide localized information on the corus numeric model outputs and therefore benefiting the downstream applications of the atmospheric modeling on the industrial side. And here we're focusing on the graded downscaling, which intuitively means the low resolution to high resolution mapping, like was shown from left to right of the figures. I feel like this laptop is not really functioning. But it's not switching slides. It's too slow on responding, and therefore, on the presentation mode, it's not really.
Okay. What do you want to do? You want to use yours?
Is the mouse available?
Why don't you take that? I copied it to the desktop, so you can take it out.
Good? Okay.
All right, sorry for the delay. So now we continue on the motivation of downscaling. So then it is basically a low resolution to high resolution mapping, like was from left to right. And then there are two families of downscaling approaches available, with the dynamical downscaling takes low resolution fields as forcings and then estimating the high resolution output by configuring regional climate models or numerical or prediction models. And then there are also statistical downscaling approaches, which do not explicitly defining the low resolution to high resolution mapping, but instead try to approximate it with historical data and under certain assumptions. And then the pros and cons of these two approaches have been well studied, with the dynamical downscaling having better interpretation by configuring a concrete numerical model, and then statistical downscaling is more flexible on matching the end user requirements. But then if we look at the disadvantages of statistical downscaling, for example, the strong reliabilities on observation, domain size, climate region, including the case of complex terrain, these disadvantages actually hurt, and this is why convolutional neural networks can come into play, because by combining with feature engineering, this is the approach that can reduce the disadvantages of known statistical downscaling methods. And then research progress has already been made since 2 years ago on the downscaling of graded precipitation with promising results. So here we use deep learning not just for fun, but also holding specific goals by answering the following research questions. So firstly, we want to know how to design convolutional neural nets for the downscaling of temperature and precipitation. And then do CNNs have generalization abilities, how the performance look like, and what the challenges are. And then here a bit of background information for convolutional neural net or CNNs. And on the most basic parts, it is a feed-forward artificial neural net with multiple hidden layers and convolutional kernels. So during the forward pass of CNN calculation, the convolutional kernel will scan the input feature map like a moving window and then summarize, for example, 3x3 grid points as a single value, and therefore holding representation learning abilities on graded inputs. This ability is the reason why CNNs are chosen in this research, so as many other real-world applications. And then based on the functionality of CNNs, we hope to do the following things in this research. Firstly, we hope to learn an effective representation of the low-risk to high-risk mapping of the target variable. And we also hope this representation to be generalizable and with no requirements on station observations. Also, in order to satisfy the above goals, we do not allow CNNs to overfit on the systematic bias of the target variable. That is to say, preserve the main function for each of the grid points and then adding high-resolution details on top of it. And then there are two variables to be downscaled, temperature and precipitation. Here we begin with temperature, or specifically the daily 2 meters maximum and minimum temperature, Tmax, Tmin. And the top-level design of the temperature downscaling is a workflow that takes low-resolution temperature and low and high-resolution elevations as inputs and try estimating the high-resolution temperature as the downscaling target with no forecasting along the time axis. And here the low-risk and high-risk are defined as quarter degree and 4 kilometers grid spacings. And here we do not, since we do not want to have specific numeric model outputs being involved with systematic bias, so the low resolutions are downsampled from their high resolution counterparts for the training, which intuitively means we let CNNs to learn the reverse of downsampling. And then about data credits. So firstly, the temperature data is obtained from PRISM, which is parameter elevation regression on independent slope model. And then the elevation data is coming from the ETOPA1, which is a digital elevation model outputs. And then for the testing stage, the NSEP final reanalysis, the FNL data, is also applied for testing the behavior of pre-trained CNNs. And here, PRISM is actually widely used in many localized studies with reliable quality, probably the best training target we can have. But before passing them into the CNNs, there are pre-processing steps we need to do. So firstly, we interpolate the low-resolution field to the high-resolution grid spacing through bicubic interpolation. So now they can match on the grid point level. And then the seasonality and heterogeneity of the temperature has been removed by the ordinary least square fit of a sine function on each of the grid points, with the two figures here showing the details. And then the fit was performed on the low-resolution temperature side and directly applied to the high-resolution temperature targets. And then the training of CNNs is separate for 4 seasons, with 2015 to 18 for training validation and 2018 to 19 the entire year for testing. And then for data coverage or the region of interest, the downscaling is mainly performed in the continental US West with complex terrain conditions. And here the domain is horizontally split into 3 components for training, tuning, and transferring efforts, with the transferring domain does not participate during the training of CNNs, which means we have train-test separation on both spatial and temporal dimensions. And with the spatial dimension separation, helps on examining the domain level generalization. And it is in general a good thing because we know that Prism is not available everywhere. So it is advantageous if we could train a downscaling model in the region with complete data coverage and then just deploy the model to another region. And then after data, we move on to the model. And there are actually various ideas of CNN designs, so we need to find one that matches our needs. And here we're specifically defining the resolution, the downscaling problem as resolution enhancements of a two-dimensional field, and it naturally shares similarities with single image super resolution. And what super resolution does is, given a low resolution image, like what's on the left, we generate a high resolution replacement of it with plausible fine-grained information inside. And then CNNs are capable of doing so, but with a performance bottleneck. This is because super resolution is a U-post problem because the low resolution input can be associated with multiple high resolution target possible. And then in the case of downscaling, we need to make it better, and we're able to do so by taking advantage of the elevation inputs. Or we say we have low resolution to high resolution mapping conditioned on the elevation data. And then for traditional statistical downscaling, they probably achieving this by calculating the absolute difference between high resolution elevation and GCM elevation. But then in the case of deep learning, we have our own way, which is performing semantic analysis on elevation and extracting terrain semantics. And here terrain semantics means the small-scale terrain features that can be represented by high-resolution elevation data, including slope and valley thing. And then this is related with the physics of surface meteorological variable, because from the flat terrain semantics and the low-resolution elevation, if they are replaced by the peaks and valleys in the high-resolution elevation, then the surface meteorological variables like temperature will change accordingly. And then CNNs are able to do terrain analyses and segmentation by having encoder-decoder architectures. And therefore, the combination of super resolution and semantic segmentation is the CNN design we're going to use. And conceptually, it means an encoder-decoder, but voice decoder has hierarchical structures that can support super resolution tasks. And then during the training of this type of encoder-decoder CNNs, the encoder can do semantic learning from the inputs by performing downsampling, and then the decoder can reconstruct the target with enhanced resolution through upsampling. And then on top of the general CNN design, we're also adding more constraints. For example, we want to have a lightweight CNN because we need the downscaling to be computationally efficient. The time window in the operational case for downscaling is actually very limited. And here we're also specifically asking for 8 times downsampling rate in total because we're downscaling from 1/4 degree to 4 kilometers, which is roughly 8 times resolution enhancement. And within the context of super resolution task, it is not appropriate to further downsample the interpolated low resolution fields beyond this original grid spacing, and therefore it's not the more downsampling, the better. And then actually encoder-decoder plus hierarchical decoder is a mainstream idea for image semantic analysis, which means we do not need to start from scratch, but instead we can modify from one of the existing architecture, and here the unit with the original plot shown as here. And the technical highlight of UNIT is the symmetrical encoder-decoded blocks with skip connections. This is a popular method that has been used in many applications, especially medical images. And here we modify the original UNIT based on our ideas of design. For example, we pin the number of hidden layer channels and hidden layers to make it lightweight. We also remove the bottom part of UNIT for specifically preserving 8 times downsampling rate in total. And from here, we have our modern data ready, and we can train UNIT to see its performance. But then there's a problem found on the fly, which is the overly smoothed outputs over the transferring domain as compared with the Prism high-resolution targets. And here we're defining this problem as the loss of high-resolution information during the domain level generalization. And here we're going to propose our solutions on the architecture side, which is an extra upper branch on the high-resolution information provider, which is high-resolution elevation. Here we name this modified unit as unit AE because high resolution elevation is already part of the inputs. So here, by having this also as output, we actually form a latent autoencoder within the original unit architecture. And then this autoencoding is useful because it is capable of learning conceptually the nonlinear principal components of the high resolution elevation, and therefore benefits the encoder's feature extraction, penalizes the decoder with overuses the low resolution representations, and also provides possibilities on transfer learning through model tuning because elevation data doesn't like high resolution temperature is available everywhere. And then the idea of units AE tuning is provided as follows. So basically, the two upper branches are sharing the same encoder-decoder base, which means under certain condition, when one of the upper branch has performance improved, we're expecting the other upper branch also has performance improved. And then over the transferring domain, when the temperature field is not available during the training, we can freeze the pre-trained downsampling blocks and then just tune the performance on high resolution elevation over the transferring domain. And then there are other implementation details for training unit and unit AE. So firstly, we cut a domain into squares with different sizes, which is called multi-scale training. This is a pretty common training technique for deep learning models. And then we standardize the croppings with Z-score, and we zero out ocean grid points. And the training is done iteratively. We usually say epochs. So for one of the epoch, it contains 1,600,000 number of samples, and these samples are bagged within 800 batches. And here we use mean absolute error loss and train separately for 4 seasons and into 2 stages. With the stage 1, we perform data augmentation and use adaptive moment estimation as the optimizer, which is an improved version of the mini batch gradient descent, and we can fix 50 epochs. And then in the second stage, we turn off data augmentation and switch to stochastic gradient descent as the optimizer and together with the early stopping. The tuning of unit AE is performed after 2 rounds of trainings. And then for the inference stage, we do not directly passing the entire domain into the CNN, but instead we segment the domain into overlapped tiles, with each of the tile having 128 by 128 pixel sizes. And here we only preserve the central 96 by 96 pixels because CNNs typically have an edging effect with the edge grid points having lower quality comparing with the central ones. And then we concatenate all the overlapped tiles and form the full domain inference. Then before moving on to the results, there is a baseline approach being proposed on temperature downscaling, which is the grid points-wise linear regression. It's a pretty simple setup for each of the grid points. There is a least square regression by taking the low resolution temperature and high resolution, low resolution elevation, basically the same input as CNNs, and trying to predict the high resolution temperature on that grid points. And then the total number of trainable weights is lower than the case of CNNs, but kind of comparable. And then this approach is backed up by the lapse relation of 2 meters temperature, and therefore having its effectiveness. But then it also has drawbacks. For example, it only considers linear relation, which may not be the best choice on downscaling surface meteorological variables. And also, it's not generalizable on different domains. So transferring domain is not the same for the baseline. It has to see the high resolution target over there. And then the result of temperature downscaling starts with a specific case on July 1st, 2018. So here for the training domain first, we actually see the 2 units can output highly like real high resolution details comparing with the present targets. But then for the right side of the panel, which has more focuses on the transferring domain, they kind of overly smooth. And this phenomenon is more clear if we zoom in. But then for the intercomparisons of units and the improved unit AE, we can see that unit AE actually does better on preserving the high resolution textures during the domain level inference. And then after the single case, we move on to the texture verification. And a bit of the motivation here, because we actually found unit AE can produce less smooth results. And this is kind of what we preferred. So then the question is, how can we quantify the smoothness of the output fields of a downscaling model? And in this research, we use discrete Laplacian for the texture verification. And mathematically, it is the second-order derivative of the inputs that can respond to the inner and outer edges of the fields. And in the one-dimensional case, the inner and outer edges are concave and convex of the curve, and if we pass a regular image into the Laplacian filter, what we can see is enhanced boundaries between all different image semantics, for example, the butterfly versus the background. And then for using a discrete Laplacian on verifying the texture of downscaling outputs, we actually do not care about the difference between inner and outer edges, but instead how the edges compared with smoothed patterns. So here we averaging the absolute value of the two-dimensional Laplacian over the target domain, and then for each of the day within the testing periods. So firstly, for the interpolated low-resolution prism inputs, which is the orange dashed line, we typically see that it has very low value and flat all the time. This is because by cubic interpolation, we'll generate perfectly smoothed output, which has no skill in the texture verification. And then if we move on to the high-resolution prism, which is a dark purple line typically on the top, it has a strong high-resolution textures inside, and it changes over time. And then when we move on to the two units, which are the red purplish lines, they're sitting below the line of high-resolution prism, but these textures are real because they're tightly following the trend of high-resolution prism during the testing periods. And then if we move on to the baseline approach, it is capable of generating strong textures, but these textures may not be real because it's not following the trend of high-resolution prism. For example, it could be an underestimation during the summer and then overestimation during the fall and the winter seasons. So the general conclusion here for the texture verification is the two units are doing better. And then in the case of transferring domain, we can see that the unit AE is having slightly more texture compared with the original units, which means the extra output branch and model tuning can make a difference in the case of texture verification. And then we've also done more traditionally quantitative verification by calculating the mean absolute errors. So here it is calculated on both spatial and temporal sides. So briefly, for the training domain, the two units, which are the purple lines at the bottom, typically showing lower MAEs comparing with the baseline approach, especially for fall and winter seasons. And then over the transferring domain, the baseline is actually better in spring and summer, but then the unit AE is doing better than the original units, especially in the case of Tmax, which means it is not just having a strong high-resolution texture, but also can reduce the mean absolute error. And then there's another part of the bias-variance analysis. We have verified the texture and MAEs, but so far, these two things have not been related. So here we think the MAEs can come from two different situations, with firstly, high bias case with underfit of the high-resolution texture, and a high variance case, which is overfit of the high-resolution texture. So here, a bit of the motivation. If we're just considering the value of mean absolute error, then these two different cases may kind of have the comparable amount in total. But then if we're considering absolutely how smooth the output is, then we don't really know whether this level of smoothness is good or not. So here we need to have bias variance analysis to connect these two things. This is beneficial on further improving the performance of downscaling model because machine learning solutions on high bias and high variance are kind of totally different. And then there are various ways to do this, and here we use two-dimensional histogram with x-axis representing the absolute difference between downscaling outputs and interpolated low-resolution inputs, and then the y-axis representing the high-resolution target and interpolated low-resolution inputs. And then if the downscaling is perfectly performed, then all the grid points should stay along the line of identical relation, with the lower left part of the panel representing the grid points that looks very smooth or look like the interpolated ones, and then the upper right panels showing grid points with strong high-resolution textures. And then the high bias and high variance signals are well separated on two sides of the line, with high variance on the right side because it means the big difference between downscaled output and interpolated output, but not so much in the case of the prism high-resolution targets, and high bias vice versa. And here from this huge array of two-dimensional histograms is organized as follows. For each of the column, it is one downscaling method, either in training or transferring domain. And for each of the row, it represents the result in one of the season. And then firstly, for the case of the baseline approach, we can see high variance signal, especially in winter and fall seasons, which means previously we've identified a strong texture on these two seasons, and the high amount of mean absolute errors are connected, and this is the high variance issue. And then for the case of the two units, we can see that the unit actually has a little bit high bias problem for the grid points with strong textures. And then unit A can fix most of it in the training domain. And also, we've noticed that the two units both produce overly smooth output during the transferring domain learning. And then the case of unit A is still slightly better than the original unit by staying closer to the line of identical relation. And then the last part of the temperature verification has involvement of the FNL data. And here we're just providing the results on Tmax with the upper panels, a specific case on July the 1st, 2018, and then the bottom plot is the mean absolute error calculated for each of the season and each of the domain. So firstly, for the specific case here, we can see that the unit and unit A kind of having consistent behavior as what they can do for downsample low resolution prism. And then for the MAE calculations, the unit AE has always the lowest value comparing with either the baseline and the original units, which means it has the generalization ability on accepting a different low resolution inputs. And also notice that here the MAEs are all pretty high. This is because FNL data has systematic bias, which will dominate the value of MAEs. And now we move on to precipitation downscaling. And basically, it's not a copy-paste of the temperature downscaling one because precipitation is a sparse variable. For example, roughly 70% of prism land grid points are zero valued. And then precipitation downscaling, which takes precipitation as both input and outputs, is actually highly affected by the level of sparsity within the data. And usually sparsity is not desirable for machine learning models because sparse inputs can form complex solution searching space which contains bad local optimas that can trap the gradient descent algorithms. And then if the encoder-decoder type of CNN is trapped, typically it's going to generate output patterns with no clear boundaries between zero and non-zeros. And in the worst case, it could be just the main value uniformed for the entire outputs. And then solutions are available for reducing the negative impact of data sparsity. So here we're listing the ones we used. Firstly, the feature engineering is possible by amplifying the data normality through data transformations. This is going to help because data sparsity is a certain type of data skewness. And then there's also a training trick, which is we can avoid the training of very dry inputs. For example, very limited grid points has non-zero precipitation values. And finally, we can make machine learning model more robust. And in the case of neural nets, it typically means less trainable ways with stronger backpropagated signals. That's going back to the architecture of units. By figuring out its backward paths, we can easily understand that the low-level blocks are the robust component of units because they can receive strong backpropagated signals. And here, just by the way, the skip connection is the thing that can deliver the backpropagated signal. And then the high-level component of units is actually not robust because the backpropagated signal need to travel lots of hidden layers to arrive here. And this is risky. And then the idea is we could reduce the number of high-level channels and partially increase the number of low-level channels to make it more important. And then this is the modified unit for precipitation, which is the figure on the left. And then on top of this idea, we could also have an alternative, which is constructively adding more hidden layers on the low and intermediate levels of the unit, and meanwhile bringing more skip connections to amplify the backpropagated signal. This idea is called nest unit in this research, and actually it is borrowed from the progress of Unit++ in 2018. This is the topology that is robust and does not losing too much learning abilities because it has deep layer aggregation with feature maps can be concatenated across different downsampling levels. And then there are also two more changes in the case of workflow and data. Firstly, we no longer use low resolution elevation as the input, but instead we use high resolution precipitation climatology because it is a better indicator for the relations between high resolution precipitation and terrain semantics. And here we do understand that high-resolution prism climatology is not available everywhere, but it is still easier to form a high-resolution climatology data than forming a near real-time one like prism. So domain-level generalization can still be expected. And also here we changed the idea of standardization. For precipitation, we use log transformation followed by min-max normalization, and the elevation is min-max normalized as well. And then for the high-resolution climatology, it is one of the prism products that's monthly calculated from 1980 to 2010. And low-res inputs are interpolated to the high-resolution grid spacings as well. And then for the implementation details, the two units are still trained separately within 4 seasons, and the training settings are similar with mean absolute error loss, multi-scale training, 2 stages, with the first stage having data augmentation and adaptive moment estimation, and the second stage go with stochastic gradient descent and early stopping. Here we avoid the inputs with more than 50% of zero precipitations, and the domain segmentation with overlap tiles during the inference stage is still valid for precipitation downscaling. And then there's one more post-processing step we need to do after the output of units, which is Reynoldian classification. And the basic idea here is we do not constrain the output of CNNs to be a specific to be strictly non-negative, which means it will generate any number in the real number zone. And in practice, they will provide some sort of negative values. And then we know that CNNs are trained with log transformed precipitation, which is not linearly correlated with the real precipitation. And therefore, it's possible that both negative and some of the low positive values can mean no precipitation case. So we need to find the thresholds to identify the two and then zero out the values below the threshold before the denormalization. And here the idea we're using is identical to the reliability diagram as the ones used for calibrating classifiers. So here we're selecting the CNN outputs over the training domain and the training periods, and then discretize the values into a finite number of bins and count the ring probability condition on each of the bin and plot the curve as the reliability curve. And then we fit on the reliability curve with isotonic regression so it can be generalizable. And we pick the thresholds, which is the minimum of second-order derivative. One example is shown here with the arrow. It's typically a low positive value with roughly 70% of ring probabilities. Actually, better options are available for sure by having concrete classifiers on this case. But here, given that the reliability diagram is working well so far, so we do not introduce other complicated approaches. And then the downscaling result for precipitation start with the case of January 19th in 2018. This is a case with massive coastal precipitation shades and also one precipitation center along the northern part of the Rockies. So if we zoom in to this part of the precipitation shades, we can actually see that the interpolated low resolution input has many bullseye-like unphysical precipitation shades, and then they are well corrected by the output of the 2 units. And also the two units can add successful high-resolution details into it by generating, for example, the narrow range shadow zone in both the transferring and the training domains. And also the precipitation along the windward slope of the mountain is well enhanced comparing with the high-resolution prism. And then we also calculated the mean absolute errors for precipitations. And basically, we only consider we avoid the case of both high-resolution prism equals to 0 and downscaled output equals to 0 because 0 versus 0 is not informative. And then for the spatial side of the MAE patterns, we can see that on the interpolated low-resolution prism, there are pretty high MAE signals along the coastal complex terrains. And also the northern parts of the Rockies. And then in the case of the output of 2 units, these MAE patterns are largely reduced. And then we've also noticed that there is a big MAE pattern on the corner of the map over the flat terrain. And here we think the units, given their training mostly over the complex terrain, they may not doing very well on downscaling the output over the flat terrain. The MAE patterns are reduced a little bit, but not very effectively. And basically, it is because they produce what they have been trained. And then the bottom part of the plot is the domain averaged MAEs on different seasons. And from the annual case, we can see that the next unit, which is the improved version, is doing better than the original units. And then both the two are doing way better than the interpolated low resolution inputs. And then the comparison of these approaches varies on different seasons. For example, during the summer, the next unit is doing significantly better than the original units. And then in the case of fall and winter, they kind of similar. And then the distribution is also verified for the 2 unit outputs. And here we're only focusing on the precipitation extremes with the histogram starting with 50 millimeters and ended with 180 millimeters per day. And then the number of bins are plotted as on a log scale with different color means different seasons. So firstly, for the comparison of interpolated low resolution prism and the high resolution one, we can see that part of the high resolution, parts of the precipitation extremes are missing comparing with the high resolution one. And then for the unit downscaling output, although it could generate high resolution details, but it is failed to capture the precipitation extremes on the right side of the distribution. And here the 2 metrics are the standard deviation and the 99th percentile value. And then in the case of next units, it is in general doing better than the original units and also better generating the precipitation extremes on the right side of the distribution. And here we also performed a test on by taking the FNL data as the downscaling inputs. And here we're focusing on the same region here. And by zooming in, we can see that since FNL data has systematic bias comparing with the original high-resolution prism, so here the precipitation shade do not looking very similar. But the fact is still, for example, the unphysical bow eye like precipitation shade that can be corrected by the 2 unit outputs, and the rain shadow zone can still be generated and compared with the original prism. And then the precipitation along the windward slope can still be enhanced, which means the 2 units are having consistent behaviors across different model low resolution inputs. And also here, the transferring domain and training domain performance of the 2 units are kind of similar, which means doesn't like the temperature downscaling. Here, the precipitation downscaling is not having domain transformation generalization issues, which does not require the tuning of unit AE, for example. And here, the FNL data also used for the comparison of distributions. And here the pattern is similar. For example, the unit is failed to generate the precipitation extremes, and meanwhile, the next unit is doing better by having the precipitation extremes really on the right side of the distribution. At the end of the precipitation downscaling is a single case on the British Columbia province, Canada. Here we do not have high resolution near real-time prism, so for the specific case, there's nothing to be compared with. But then looking at the details of the output of the 2 units, they can still correcting, for example, the BOI like precipitation shades, and to the one that more related with the impact of orography, which means their domain level generalization is still valid. And here comes the summary and conclusions. So we've answered all the research questions before. So firstly, for the effective design of CNNs in downscaling, here we found that encoder-decoder CNNs with unit-alike architecture is doing pretty well. And then the performance is promising in the case of texture and quantitative, like MAE calculation-based verifications. And also, the CNN-based downscaling is confirmed to have generalization ability across different time, domain, and inputs. And finally, different downscaling targets have different challenges. For temperature downscaling, one of the challenges is the domain-level generalization for preserving high-resolution details. And for this part, we use a unit with an autoencoder on high-resolution elevation tuning to solve the problem. And then for the challenge of precipitation downscaling, it's mostly data sparsity. And here, the borrowed idea of nest units is doing better than the original unit, which means it makes a difference. And this is the end of my presentation. Thank you for coming.
Kyle.